All right. So today is one of those weird days where everyone has decided to sit over here for some reason. It's kind of weird. It's like, somebody must smell good over here. All right. So today we're going to continue talking about file systems. Last time we got through path name resolution, and we'll review how that works, and then we'll talk about how we actually find the data blocks, right? So we've talked about the process of translating a path name to an inode, and now we're going to figure out the other part of it, right? So we've got to the top level of the data structure that holds the file content. Now the user probably wants us to find the bytes that are associated with that file. So we'll talk about how to do that. All right, so you guys are done with assignments 0 through 2. So I don't know, give yourself a little round of applause or something. I mean, and actually, I don't have a slide for this. I should, but let's have a round of applause for the course staff. There we go. Yeah, it was really great to see Guru, Jinghao, Zihei, Carl, John, Scott. Everyone was there. It was really cool on Monday night. And again, I'm sorry I had to leave early, but I don't know. I turn into a pumpkin at around 9 o'clock these days. So, all right. So these are statistics I just pulled up quickly from the website. The problem with these numbers, I'll just state up front. I know people want to see these. I understand why. I'm going to show you these. These probably include people who have dropped the class. So there are some low scores here that may be pulling down the mean and median, but this is of everything that was turned in by anyone who submitted anything, right? So assignment 0, people did pretty well on, obviously. Assignment 1, also people did okay. Assignment 2, a little more of a struggle. And again, if you filter out some of the people that didn't turn in anything, particularly for assignment 2 and assignment 1, those numbers are probably a little bit higher than they look, right? I wish I had printed this out, there were something like almost 30 people who earned a perfect score on assignment 2. So who turned in a patch. Yeah, I'll give those people a round of applause. I don't know who they are. But so there were a number, and there were a number of people who turned in, patches that earned over 70 points. Remember that this is for the entire assignment. This is not just the implementation section, right? So there were people that turned in quite well done assignment 2. So I was happy to see that. So at this point, one other announcement. We're working on grading the midterms. We're going to try. My goal is to have them back in class next Friday. I know this is a while since the midterm took place. I'm sorry about that. I'm not super sorry about that, though, because you guys know what the TAs have been doing over the last week. So I think that you guys would have preferred to have them helping you with the assignments. So that just means the midterm is going to lag a little bit. The other thing is, and I wish I had this up on this slide, the calendar for next week, for the rest of this week and next week, has been altered a little bit. I've removed office hours that are normally held by Zihei and Jinghao, since they will be grading, right? So that we have fewer office hours for the next week and a half while we try to wrap up the midterms. And catch up with all the grading for the code reading questions and design documents that are still there on the website. All right, any questions about assignment status at this point? Yeah, Adam.
See, a lot of people could exact.
I mean, if you got over 70 points, I think you pretty much had to get exact to work, right? So I think there were some groups that did that. I don't have it broken down specifically. We could look and see how people did on like the ARG test or something. So, but yeah, I think there were a fair number of people who got stuff working. So that was good. All right, onward. So assignment 3 has been out. I don't remember when it's due, but I think you guys have about 5.5 weeks or so to work on assignment 3. Assignment 3 is harder than assignment 2. Assignment 3 is also more fun than assignment 2. It's more interesting. I know. How can that be possible, right? How could anything be more fun? Trust me, I promise you, it is way more fun than assignment 2. All right, so I know I said I wasn't going to do this. And I'm going to do it in a way that maybe will frustrate some of you guys. So how many people here have an assignment 2 that's not completely working? OK. So if you have I'm going to give you guys a choice about how you want to approach assignment 3, right? Because what I don't want people doing is sort of like giving up, dropping the class, resigning because they're worried about. I will admit, I did warn you guys repeatedly about how difficult the assignment was, and I don't feel like everybody took those warnings to heart. So in the aftermath of assignment 2, I think if some of you guys had been working at the rate you were working for the last couple days for like a week or maybe even 10 days, you would have finished the assignment, right? But I think you guys maybe now have a real understanding. I realized in retrospect, I should have let you guys get closer to the deadline the first time before extending it. I think that would have been more effective. Maybe something to try next year. So for assignment 3, I want people to try assignment 3. Okay, it's a cool assignment. It's fun. It's interesting. It's going to require you guys to do design in a different way. I think it's a lot cooler than assignment 2. It's a lot more fun to get to work, right? But if you don't want to start with your broken, cobbled together assignment 2 that you started working on at noon on Monday, here's the deal I'll make you. I will give you the assignment 2 solution set. You have to give me 50 points. Okay, that's the deal. And there's a couple reasons for this. First reason is I want to reward the people that actually did assignment 2, right? I told you guys you had to use your own code base. If you want to go forward without the penalty, that's totally OK. If you want the solution set, you'll have to email the course staff. We'll put a note in our little book. And at the end of the semester, your total grade for the course will have 50 points subtracted from it. 50 points is about half of the implementation grade for assignment 3. Assignment 3 is worth 200 points. Half of it, 100 points, is for the implementation. Part of the reason for choosing this threshold, however, is because, and I wasn't sure whether I wanted to admit this in class, if you just submit the assignment 2 solution set for the assignment 3 auto grader, you get like 30 points. Because some stuff works, right? It compiles, it runs, some of the tests pass, the stability tests work, a bunch of stuff fails, right? So you get 30. But you don't get 0, right? So this number needed to be bigger than that. Otherwise, I'm just giving away points, right? So here, if you want to start with the assignment 2 solution set, that's fine. But you will lose 50 points, meaning that you will have to do better than 50 on the assignment to break even, right? Any questions about this? I think this is fair. There are people here who turned in very good assignment 2s. I think you guys should continue using those. The drawback of working with the solution set is that you didn't write it. So you have a whole big new blob of code to work with. The upside is obvious, right? The other thing is that I have a little incentive for people who complete assignment 3. I don't know what the cutoff will be. It might be that you have to get a perfect score from the auto grader. But anyone who manages to do that, at the end of the class, I will post something on Facebook with mentioning your achievements, and I will mention some people that I know on Facebook as part of that post who might be interested in finding out how well you guys did on these assignments. So that is my carrot for people who want to complete assignment 3. In order to be eligible for this offer, you have to work with your own code base, right? If you take the assignment 2 solution set, you're out of the running. All right? I really want people to do assignment 3, if that's not obvious, right? So there's a couple of new tools here. Think this over. You guys don't have to make a decision right away. If you want the assignment 2 solution set, email the course staff. We will send you a working assignment 2. It'll be up to you to sort of figure out how to get that into your tree, and you're welcome to continue to use that as you work on assignment 3. All right, any questions? Yeah.
So even though we are still need to finish assignment 2,
yep.
Is there a way that we can use the auto grader to make sure that our assignment 2 is caught up?
Good question. So in theory, yes. In practice, I don't know if I want to turn the autograder back on because I'm not sure. The website is a terrible hot mess of code that I've just tried to and yeah, I know it's my fault, but I've also just tried to stay. I don't want to try to fix things this year. I'm just leaving things alone. So I'm not sure. In theory, is that hard to do? No. In practice, you can run those tests yourself. Right? That's what I would suggest. Right? Is just run them from in your own terminal. And if you guys want a very specific breakdown of what we do for assignment 2, I'd be happy to provide that. They're pretty. I mean, we don't run any magic when we test your assignments. We're running tests that you guys already have. Right? Sometimes we do a little bit of stuff like compile special versions of tests or whatever, so we don't have to pass arguments in case your argument passing doesn't work. But in general, we're just running things you guys already have. Right? Yeah, Adam.
Where are the correct outputs for the test? I've only been looking at the OSCE.
I mean, oh, that's a good question. I'm happy to post for most it's obvious, right? For like the stability ones, I guess it's not. Yeah, if you guys want to know what the autograder is looking for, I'm happy to tell you. Right? I mean, in most cases, it's like it didn't crash. Other times, it's looking for some string that's printed like success, right, or complete, or it's looking for things like uh-oh or failure, right, or for stuff to panic, right. So yeah, you're right. Some of it's obvious, but the tests all these tests were really designed to be used by people, right. These tests were originally, the way the autograder used to work is that the autograder, namely me, used to sit down with a bunch of your assignments and run these tests by hand and look at the output and figure out what happened. So the tests are actually written to be used by human beings, right, not by a computer. So hopefully their output is not incredibly hard to parse. Yeah.
Some people are unfortunate enough to only get 45% of assignment 3 implementation. Will they actually lose points?
They will. Yeah, so if that's the thing, right? If you take the assignment 2 solution set, this is part of the plot, right? This is intentional, right? You have to get about 20 points, extra points on the assignment in order to break even, right? I don't want people to take this, you're committing to working on assignment 3. I'm not giving you the assignment 2 solution set so you can get free points on assignment 3. I'm giving you the assignment 2 solution set in hopes that you will do assignment 3. Right? That's why there's a gap between what you'll get and the points that you're being charged. Right? It's a good question. All right, yeah. I just answered that question. I mean, in theory, yes. Right? In practice, will I get this implemented? Probably not. Right? I think it's, and again, you guys are welcome to run those tests at your own convenience. I mean, especially for assignment 3, I would suggest that you guys do more testing locally because the assignment 3 test takes some time, right? The assignment 2 tests tend to complete quite quickly, but if your system is broken, it can spend several hours being auto-graded for assignment 3, right?
Oh.
Yeah. I mean, most of it. Yeah, I would say almost everything. I mean, assignment 3 assumes that all the user space tools work, right? So really, if you're not returning the correct error code in certain cases, so some of the stability stuff, it's possible you could lose some points on like bad call or whatever and still do okay in assignment 3. But in general, assignment 3 picks up where assignment 2 left off, right? You need fork, you need exec, you need all the process stuff, you need wait, you need to be able to print to the console, so you need read, write, open, close, etc. Right? Assignment 3 isn't designed to stress test those things, but it does assume that they work. Right? Any other questions about this? Okay, so back to, yeah?
What would be the ways that you would apply for something? How would we ask for this? Is it like an online?
Email the core staff. Yeah, if you want the solution set, email us and we will send you the tarball. Yeah. I actually don't love the way the solution set is implemented, but I didn't write it. So, but it does work. So. Any other questions? Now, just one final sort of warning or word to the wise, when we test when we run the cheating detection on your assignment 3s, we will be cognizant of who had the assignment 2 solution set and who did not, right? And plus, I mean, if you take the assignment 2 solution set, you have no incentive to give it to someone else, right? Make them take the 50 points, right? Otherwise, they're just, they're getting the benefit without having to pay for it, right? So I would suggest that you not distribute that among yourselves. You can certainly read it to figure out, how it approaches assignment 2 and the types of things that the solution set does and how it solves some of the problems you guys are having, right? But don't give it to somebody else to use. All right, so any questions about inode? So last time we talked about inode structure and a little bit about the structure of directory files. Any questions about this before we go forward? I've already lost a little bit of time, so let me just, right, so you remember, just a brief review, ext4 inodes, 256 bytes. We need to know where the file data blocks are. We're going to talk more about this today. The inodes contain permissions, timestamps, and they're all named and located by number, right? So how did we find inodes? I need to be able to locate an inode by its number. In ext4, how do I find inodes? How do I translate an inode number into the 256 bytes that are associated with that inode? Yeah?
Start with the root.
Well, you're doing path name translation, right? I'm saying inode X. Where are the 256 bytes for that on disk? No. No. It's a data structure question. What data structure did ext4 use to store inodes? Yeah.
They're stored in specially allocated blocks.
Yeah, OK. We're getting closer. Bitmap was used to store the ones that were allocated into freed. No, now we're going colder. They're stored in arrays, right? And remember, we could have put them in one array starting at the bottom of the disk, which means you would take disk start block, plus 256 times inode number to figure out which byte the inode started at. Actually, remember that ext4 put multiple chunks of inodes throughout the disk, right? And this was because if we put them all in one place, the inodes would be located far from the data blocks, right? And most of the time, file operations require modifying or reading or using both the inode and the data blocks associated with the file, right? And the result of this was also that we had a fixed number of inodes per file system that we could potentially run out, right? Directories were a special file that essentially stored a mapping between path name components and inode numbers, right? So the relative name, the name relative to that particular directory. We showed some examples of this. This is boring. Right? And the process, as somebody pointed out, the process of translating a name to an inode number. We started with the root directory, which is inode number what? 2, for some reason. Right? Which we know. And then we essentially just open up inode number 2. It's a directory. If it's a directory, the directory has a structure allowing us to map the next path name component. Right? We do this repeatedly until we end up with something that's a file. Right? The last component, well, it could be a directory. We could be opening a directory, right? But we'll probably open it in a file. Right? So the last path name component probably doesn't point to a special directory file. It probably points to a data file. All right? All right, any questions about this before we talk about data blocks? Yeah, Kevin.
Theoretically, I'm not saying it's not something that you just require open to take an inode number instead of a relative path name that, like you can open an inode number or whatever, or is that a dangerous and terrible idea?
You could probably open something by inode number. I wouldn't, it's like, does anyone remember CompuServe? Is that like way before your time? I can't remember, it was like one of the early email providers decided that people would like an email address that was like a phone number, right? So your email address wasn't like, Kevin@gmail.com. It was stream of meaningless digits at gmail.com, right? Because people are used to phone numbers, right? It's like, no, phone numbers are terrible, right? So yeah, you could name them that way, but that would be difficult for humans to use, I think. But I don't see any sort of security problem with allowing someone to open an inode number, right? The path name in some way is just a more human and intuitive way of naming inode numbers, which the computer wants to know about. OK, good question. Anything else? All right, so now once we're able to actually locate the inode for the file, then most file operations actually want data, right? We want to figure out where the bytes are, or we need to figure out where the bytes are for a particular file, right? So we use the path name, we find the inode number. Now we need to find the data blocks that are associated with that file, right? And any sort of read or write has to figure out, how do I, I'm going to give you an offset into the file. How do I map that offset to a data block, right? So keep in mind that files can be sort of accessed in a random way, right? I don't have to read the whole file. I can write an arbitrary byte of that file if I use lseek properly, and the file system needs to be able to support that, right? So I need to support such a sort of random access to files. Why is this hard? Why don't I just lay out my files as a big array of data blocks? Done. I'm just gonna wrap this up and go start implementing my file system that lays out files as a just big array of data blocks, super fast. Why doesn't that work? Yeah.
So when you try to extend the file, you might not be able to get another contiguous piece of block.
Yeah, what do we call this? Yeah, you guys remember fragmentation, right? Same problem here, right? Except a lot worse, actually, potentially, because I could have a file that started out with 1 byte, now it's got a megabyte, right? Where does that extra data come from? Trying to keep now file systems do try to keep things close together, right? That's a good design strategy in general, so I don't have to seek all over the place. But at the same time, I need to be able to allow files to grow and shrink without creating terrible fragmentation issues, right? All right, so let's talk about a couple different data. So now we're talking about a data structure, right? The inode contains a data structure that allows me to map an inode, an offset to a data block, right? An offset, any offset within the file is stored in some data block. How do I figure out which data block corresponds to a particular offset, right? So one way of doing this, is a linked list, right? The inode then contains a pointer to the first data block. What would that pointer be? I mean, we can call it a pointer, but what would the pointer actually be? Yeah, it's a block address, right? It's the data block number, right? Which block on disk has, the first data block for this file. And then essentially the structure that I use within the data blocks themselves has now a pointer to the next data block, right? So I'm going to lose a little bit of space in each data block because I need this pointer, but now I can organize my data blocks and I can essentially have a file that can grow and shrink, right? What are the pros of this approach? Yeah. What's that? Yeah, so this grows nicely. Well, it's simple, right? And there's a small amount of information in the inode, and there's also a small amount of metadata. And the metadata grows, right? The metadata here are those inode numbers that now have to be embedded in each data block. But that grows, nicely with the size of the file, right? So that's nice. What are the problems with this? Yeah. Yeah, remember this whole thing where I wanted to be able to map any arbitrary offset within the file to a data block? Now every time I do that, I've got to walk this whole data structure, right? Potentially from the front if it's on a doubly linked list, but it's bad, right? Don't know how far I need to go. I'm jumping all over the disk potentially. So this is not necessarily a fantastic idea, right? All right, so this is starting to look like our well, what other data structures is starting to look like that we talked about? Page tables, yeah. What's the difference with page tables? It's going to look similar to page tables for like another moment or two, but what's the difference with process page tables? What advantage did I have when I was doing page tables? Yeah. Yeah, not just contiguous. What's the difference about process address spaces versus files? Doug?
Process address space is unique to each process, whereas the file system has to be shared by everything. So you don't have the same, translating, I guess.
Not quite. That's not what I'm after. It's two things, actually.
There will be entry for each data block.
Yeah.
Page table, we had the option to move one of the page.
Well, maybe, but what, we're getting closer. What created that? Gino?
We had a TLB to help us translate things through hardware.
Well, that's a difference between VM and file systems. So now about these data structures. There's two properties of address spaces that files don't have, right? What is one of them? Yeah. We're so close. Yeah, Kevin.
Files have to be able to grow dynamically.
Yeah, address spaces are all the same size, right? So that's one thing. But what else about address spaces was a problem with page tables that files don't have? It has to do with locality. Yeah.
The slapping is stepping up?
Not really. Address spaces are sparse, right? Most of the address space is not used. With a file, that could be true, but you would hope not, right? You would hope like you don't have, a gigabyte file allocated, but there's only a megabyte of content hidden in there somewhere, right? I mean, that would be kind of dumb, right? So files, grow as the amount of content in them grows, right? And you're trying to, again, hopefully you keep files about the size of the data that's actually contained in them. Address spaces were all the same size. Most of that was unused, right? But the data structure, so this data structure has this additional requirement that it has to potentially allow a lot of different sizes, right? Where address spaces, we were trying to deal with sparsity, right? But this gets close. So a second approach here is I can put all the data blocks in the inode, in a single array that's allocated when the inode is created, right? So what's nice about this? What's fast about this? Sonny? It's fast, right? What is fast? Looking up offsets, right? It's also simple. And offsets, I can just convert an offset to a data block and figure out exactly which inode contains, which data block contains that offset in sort of one lookup, right? What's wrong with this? Lots of things. Yeah. Well, I would actually think on today's systems, most of the array would be used. But why is that, Doug?
Because it's an array, it doesn't grow well, and it takes up a lot of space.
Doesn't grow well, right? Doesn't grow at all, right? My inodes are fixed size, right? So this essentially means that I can only have a fixed size file, and essentially, the inode size now directly determines the size of the file, right? And yeah, I could allocate huge, massive, like 2 megabyte inodes just in case somebody wanted to create, a 2 terabyte file. But that would be kind of dumb, right? So we want a data structure that isn't sized to the maximum size of the file. Interesting. We want something that can grow and shrink, right? So the data structure, the metadata that we're storing here has to some degree, grow and shrink with the size of the file, right? And as someone pointed out, that was correct, actually. I didn't mean to say it was wrong. If I allocate an array big enough for a huge file, then a lot of small files won't use most of it. Right? So I have a problem here. If I make the array small, I can't have big files. If I make the array huge, small files are wasting most of the space. Right? All right, so what a lot of file systems were designed around is this assumption. And it's interesting. I don't know how true this is anymore. But it would be interesting to find out. The observation is most files are small. And in many cases, I think on systems, this is still true. Why is it? Why is that? Why aren't most files massive? Yeah, Doug.
Wait, most files? Oh.
Most files are small.
Wait.
Yeah.
Well, some are directories.
Okay, well, actually, that's a great point, right? So a lot of files are actually directories. Directories aren't that big, right? They only have a few entries. What else? Yeah, there's all these like stupid little system configuration files all over the place, right? Maybe on Windows this isn't true, right? Because Windows has this registry hack thing, right? Where it's like all the metadata ever needed by any process on the system is stored in one huge disorganized database, right? The performance of which starts to bottleneck the entire system, right? But anyway, it's a small digression. Not to say that the Unix way of doing this is better, right? Which is 10,000 differently formatted configuration files littered all over the system that you'll never be able to find, much less figure out how to modify without something crashing, right? But anyway, the point is that a lot of files are small, and those small files are there for a variety of reasons. configuration information, small pieces of metadata, whatever, right? But again, on certain modern file systems, I think it would be interesting to do this, to profile this again. I'm sure people have done this. I should look this up, right? So the way I respond to this is I say, OK, I'm going to have the inode store some pointers directly to data blocks, right? So the inode is going to have some references to direct references to data that is part of the file. On some file systems, they actually went, I think we'll talk at least about one of them, they went a step further and they actually had data right in the inode, right? So they're like, ah, man, 256 bytes, I've got all this wasted space, right? What if I have a 2-byte file, right? Just jam that data right into the inode, right? That way I never have to even look up a single data block, right? But OK, let's talk about something a little less weird. Actually, that's not a bad idea for tiny files, right? But the inode stores some pointers to blocks. We refer to those as direct blocks, right? They're directly referred to by the file, by the inode. The inode also has pointers to blocks that themselves contain pointers to blocks, right? Those we refer to as indirect blocks, right? What do you think comes after indirect blocks? The doubly indirect blocks. The mythical, fairly, rarely seen doubly indirect block that contains pointers to blocks that contain pointers to blocks, right? And then, what's next?
Triply.
Yeah, this is like the white whale, the triple. Well, you can imagine what this goes, right? The triply indirect block, which contains pointers to blocks that contain pointers to blocks that contain pointers to blocks that contain pointers to blocks. I think. All right, right. So you can scale this up ad infinitum, right? And what it ends up looking like is a longer version of this, right? This is my inode. This is a direct block. It's referred. These two are direct blocks. This is a indirect block, or sorry, these are indirect blocks, right? Because they're one hop away. And this block of data, which is also going to be 4K block, contains essentially all pointers to data blocks. The other nice thing about this, if you like powers of 2, is that the data blocks now only contain data, right? The linked list, you had to have like a little metadata in them, so each block would have like 4,094 bytes of data in it, which is just terrible, right? It's just going to make you very sad, right? Whereas here, it's like everything has 4K, right? So nice powers of 2. What's nice about this? Yeah, Gabriel.
I'm just wondering where the internal nodes there, are those data blocks or
Yeah, so technically those are, so the question is, are those data blocks or inodes? I don't want to call them inodes, right? They don't store data, so they're not a data block. They have they're not visible to anyone other than the file system, right? So these are now metadata that the file system stores. This part of the system. So it's an interesting observation. As you create a huge file on your file system, the amount of space taken up by the file is not only the amount of space needed to store content, but also all the extra space that you need to store these data structures that allow you to map offsets to data blocks, right? Good question. What's nice about this? Yeah. Yeah, and the index scales with the size of the file, right? And it's to some degree it's a little more efficient and faster for smaller files, right? As files get big, it takes me longer to actually map the offsets, because the offsets, more and more of the file is going to be in parts of the file that are mapped by doubly or triply or quadruply indirect blocks, right? But offset lookups still are only going to take a couple of hops, right? And if I'm working in a particular part of the file, I'll be working within the same sort of doubly or triply indirect block, right? You can do these calculations. It's like if you say, you say that each block's 4K, each inode is 4 bytes, so each block of pointers contains 1,000 pointers to data blocks, so each block of pointers now maps 4 megabytes of file, right? And as you go up, like a doubly indirect block could map like 4 gigabytes of file. Yeah.
Is it the case that you can keep some metadata on how frequently the blocks are accessed and migrate those pointers to the top level inode? So
Well,
you don't have to actually jump as much?
Yeah, well, the problem is, remember, this is an order, right? So, Yeah, that's important. That's important to realize. Yeah, there is order here, right? So essentially, there is order in this chaos, right? So this is, the first 4K of the file, second 4K, third 4K, right? And essentially, this, if you wanted to enumerate the file, you would start with the direct blocks, right? Then you would start with the indirect blocks. Then you would start with then you would continue sort of down. So you can't move data blocks around in this hierarchy, right? Because that would break unless you were swapping pieces of the file. Yeah, and by moving content, right? And the nice thing is that small files stay small, but I can support arbitrarily large files. I think there is a file size limit on current versions of ext4, but I think it's in like petabytes at this point. So I don't know. I used to think I would never have a file that was like a terabyte, right? Petabytes. What would you have in a petabyte file? Okay, so now, and this is this is essentially as far as we're going to go with these data structures. My guess is that some of the fancier I think RiserFS uses like some sort of fancy data structure to store this sort of thing. So there's certainly other data structures you can use to store information about data blocks, but this is as complicated as we're going to get. Gabriel.
Does it do any sort of rebalancing of the tree?
Yeah, so that's the other question, right? And I guess you could technically, right? Because you could have different depths at different parts of the file. Does this slide do any rebalancing of the tree? No, right? But in theory, you probably could. I don't know how much of a performance improvement it would get. Yeah, but again, I think there are modern file systems that replace this with a little bit of a snazzier data structure. Any questions about locating data blocks? All right, so one of the, before we start talking about, next time we're going to talk about this, hopefully, I don't know how far we get today, we're going to start talking about a specific file system, right? But before we do that, let's talk about a couple of things that most file systems try to do, right? One is not be super slow, right? Again, like slowness is not a selling point of a file system, right? So, system design principles, how do we make a big, man, I didn't even get it. You guys are well trained now. It's like I get 2 words, like Jeopardy. It's like hitting the buzzer. How do we make a big slow thing look faster? We put a cache in front of it, right? Or put a smaller, faster thing. Usually the thing is smaller and faster, because if it was bigger and faster, why are you using this slow thing, right? Put the data on the fast thing. Yeah, maybe. Right. Well, okay. Maybe smaller, faster, and cheaper. Some combination of those things, right? So, and part of what's interesting, what we didn't talk about with memory management is there is a portion of the memory on every modern computing system that is not memory, right? It's not being used as memory. It's being used as a cache for the file system. We refer to this memory as a buffer cache, right? This portion of memory contains buffers that is essentially buffering data for the file system. Right? And there are some interesting performance implications for modern systems in terms of determining how to balance memory used on your computer between memory that's holding pages for address spaces that are in use by processes and memory that's actually caching file data. Right? And modern systems will rebalance this division as the system is used based on load. Right? If you have something that has a huge amount of file system access, you'll probably find that your system is caching a lot of file data, right? Because that makes that fast. All right, so yeah, okay, I just said this, right? So you can think about the extremes, right? So if I have a big buffer cache, let's say I set this up statically, and what I did is I configured my system to use most of its memory to cache file data, right? The problem is, if process address spaces start to get big, then I start to thrash, right? And I can, cause my file system performance is great, right? But I might start the disk is going to start to kick my butt here again, right? Because think about it, I've spent all this memory to make the disk fast, but what part of the disk is now going to be slow? The disk is also involved in what? Swapping, right? So it was like, sweet, I have all this memory, going to make the disk fast. And it's like, actually, the swap file is now ruining the performance of your entire system, right? If I do the opposite, right, and I use most of the memory to store process pages, right, then I might not have any problems with swapping, but file access can be really slow, right, because most file accesses are missing the cache and going to disk. Yeah, Ed.
So wait, swap memory wouldn't end up in the buffer cache, would it?
No. No. The swap, yeah, you don't, yeah, I have to think about that more. I don't think, you wouldn't buffer writes to the swap file, right? Like when things go to the swap, they're going to swap, right? You're putting them there because they can't fit in memory. So you're going to remove them from memory. Stuff that's in the buffer cache is data that is or will soon be on disk, right? So yeah, that's good. You can almost think of memory, the memory that you use it as memory as a cache of the swap file. Weird. But I wouldn't think about it that way because that's confusing. And on Linux, there's actually a weird kernel parameter called swappiness. It's actually called this, right? If you want to set it. I think it has 2 P's. Maybe it's just one. Anyway. And that essentially what this controls is how aggressive is the kernel about swapping pages out, unused memory pages, in order to reuse that memory as buffer cache, right? So the boundary, the division between memory used as memory and memory used as the buffer cache is sort of constantly fluctuating. And this parameter controls how aggressive Linux is about reusing memory as buffer cache, right, and swapping it out. All right, so let me think. I don't even know if I want to do this or not. You know what? I'm not going to go through this year. I don't care. This is a design exercise we did last year that I'm not that interested in. So let me point out what most systems do. Last year we went through a little bit of an example of where to put the buffer cache. You could buffer at the file level. Where most buffer caches go is they actually buffer data blocks, right? So the file system operates the way it normally would, but when it reads or writes data blocks, whatever they are, right? If they're inodes, if they're data blocks, those reads and writes actually hit in this buffer cache, right? So the buffer cache buffers disk blocks, right? Those disk blocks could be either inodes or data blocks, right? Okay. So let me talk about consistency, right? Where to put the buffer cache, don't worry. It goes below the file system, right? It caches disk blocks, right? But what it does mean, again, is that the file system, when it's operating on something that is actually a disk block, when it says read or write this disk block, those reads or writes may actually be lodging in memory, right? So remember, the other thing, it's not just being fast, right? I mean, a file system could be very fast and just store all your data in memory, right? The problem would be what? What would be the problem with, let's say I just mount my file system in memory. That would be awesomely fast. Yeah, Adam.
If we're going to write to a data block, isn't the data immediately going to be inconsistent?
Yeah, so it's more than this, right? So remember, now because I have a cache, some of the write or read operations that file systems are performing are going to be served from the buffer cache, right? So when the file system says read this data block, right, what's actually going to happen is the operating system is going to perform the read, but it's also going to load that data block into the buffer cache. The next time I read from that data block, that read is served from the buffer cache, right? So it doesn't actually have to go to disk. Same thing with writes, right? When I write a buffer, a data block to disk, the first time it might go all the way to disk, but I also save the contents in memory. The next time those contents may be only updated in memory. What problem does that cause? Yeah. Yeah, so anything that's in the cache that's not on disk, this is sort of analogous to dirty pages, right? But anything where the block in the cache is different than the block on disks, the block on disk, those are going to be lost if the power suddenly goes out, right? So if suddenly, somebody trips over the power cord, anything that's dirty in the buffer cache is going to be gone, right? Yeah, Tom.
You might want your operating system to load into memory if you're doing like a recovery, for example, right?
I mean, there's times when I wasn't being entirely facetious. There's times when you actually do want to mount file systems on memory for a variety of reasons if they need to look like a file system and not persist across reboots, right? And then remember this as well, right? So train the consistency problem. Did I answer your question?
Yes.
Yeah. Remember that every file system operation requires modifying a bunch of different data blocks and inodes, right, and other file system data structures, right? What's an example of this based on the data structure that we just, let's say I append a huge amount of data to the end of a file, right? I obviously need to find some data blocks to store that data. What else do I need to find? What other data structure is going to need to be updated? I need to update the size and the inode and things like that. But when we walked through that before, but now that you've seen how I map offsets to data blocks, what else do I need to update? I need to add stuff to that tree that I have, right? To my sort of multi-level index that I'm using to map those offsets. I may need to allocate some doubly indirect blocks, right? And then some singly indirect blocks pointed to off of those, right? So I have some data structures that need to be updated as well, right? And we went through this before. I need the data blocks. I need the data structures. I need to modify directory files, write the data, right? So all this stuff's happening. And if some of these things, so now remember before we said, well, pick a couple of these that don't happen and then see how much trouble your file system is going to get into when it tries to recover after some sort of failure. And now the problem is because you have a cache, it's possible that any number of these can not happen, right? Some of them may go all the way to disk. Others may be cached by the operating system. That's trying to be helpful, right? The operating system is trying to make things fast. The problem is that sometimes this causes a problem with consistency, right? And yeah, we just talked about this, right? And to some degree, so what operating systems are going to do is that obviously this is a file system, right? So would I cache stuff in the, if I'm going to use memory as a cache, would I cache dirty buffers forever? I mean, where does that content eventually have to go? To the disk, right? The question is, when do I put it there, right? And there's and to some degree, if we think about there being a window here, there's a window of time where the contents in the cache and the contents on disk are different, right? During that window of time, if there's some sort of catastrophic failure to the disk, I can leave myself in an inconsistent state, okay? What's the safest way to maintain the consistency of the file system? I now have a cache, but what is the safest way to maintain file system consistency? Tom?
Somehow save to the disk. Like, the only thing I can do is like when you're writing a document, it like sometimes auto-saves.
Oh gosh, no, we're not talking about Microsoft features. Yeah. Yeah, so the safest approach is don't buffer writes, right? It turns out that we actually do buffer writes. The write will update the buffer cache. Why? Even if I'm going to write it to disk immediately. Yeah, Gino.
Did you try to read from the, it's still safe to read from that buffer?
Yeah, I want it in the cache in case the next thing that happens is I read from it, right? So I can still add it to the cache. That's safe to do, as long as I immediately write it to disk. Right? So every write, every update to that data block will both update the buffer cache contents and be immediately sent to disk. Right? So this is what's called a write-through cache, right? Because writes go straight through the cache. What's the least safe approach? That maintains the consistency of the file system, right? Not writing is not an option, right? That's broken, right? But how would I wait the longest, Adam? No, I mean, that's close, right? So I could write all the stuff to, but what would I be missing? Yeah. Okay, file close. You're still not getting enough data blocks to disk. When do I absolutely have to write a data block to disk? Yeah. That would cause this, but when specifically? When the block is evicted from the cache, right? Remember, this is a cache. It only caches a portion of the file system. When I remove a block from the cache, then I can write the contents to disk. To some degree, that happens when I shut the system down. You can think of that as a special case. I'm removing everything from the cache because the cache is no more. And we call this a write-back cache. So a write-back cache essentially makes this interval the longest, right? 1 more minute. What is a... So obviously, safety wins here, performance wins here, because this is doing the smallest amount of writes for a particular workload, right? What's a potential middle ground here, right? Let's say I wanted something that's less aggressive than my write-through cache, more performant, less daring than the write-back cache, more performant than the write-through. Yeah, Doug?
Right whenever the disk isn't terribly busy.
Yeah, okay, but what would that be a variant of, right, Gino?
Right to the disk whenever you write from the disk, right?
Well, but that's really an update, right? So that would be here. Yeah, Kevin.
Write it at intervals.
Yeah, so I can essentially, okay, there's actually 2 things, right? So one thing is I could write periodically. The other thing that some file systems do is I always update metadata. Right? We'll talk more next time about why this would be the case. But you can imagine that certain file system data structures have to stay consistent even if the data in the file doesn't, right? All right, so we'll pick up this on Friday, and we'll probably start talking about FFS as well.